I think I'm the president of the. ¿Quieres que te oiga? Sí, es que no pusimos. Okay, so now, please go ahead with the presentation.
Okay, so I'm going to present now complex representations in deep learning from algorithmic information to autoencoders and hypernetworks. Okay, so this is one that works. Yes. Okay, so I'm going to first go over algorithmic inference, then statistical inference, which I will see the connection, variational models, and finally hypernetworks. Okay, so first the research questions and a bit of motivation. Why am I doing this? How is algorithmic information related to deep learning? I think this is a fundamental question, and it algorithmic information theory is a theory about computation, and computation is a very general thing, as we will see now. The variational autoencoders are essentially a very general way to coarse grain information, which is a very general thing that we do here in complex systems. So it is a very nice thing to be able to do in this way. And Hopfield networks are also a general thing that when we connect those two things together, we get a better way to learn those abstract representations of data. Okay, so meta-learning is a way to increase flexibility of those models, and it is connected to the things above in that we are trying to predict those next frames, and we are going to do prediction of next frames using those complex representations. Okay, so let's start with algorithmic inference. First, let me introduce just Bayesian inference recap. Okay, so it's just a way to update probability of hypotheses. Okay. We are interested usually in the marginal, and the hypothesis class can be just whatever. For algorithmic information, we are considering the hypothesis class of Turing machines. Turing machines are a very general thing. There is the Church Turing thesis that says that anything that is Turing complete can simulate any other thing that is also Turing complete, including itself. Okay, so from very simple rules, we can essentially simulate any other thing. We don't care. Once we have simple rules, the complexity of the system is maximal in some universal sense, right? So Turing machines are a particular instantiation of this kind of thing, which is essentially based on having a state space, which will control a tape and read and write symbols to it while moving the tape back and forth. So to complete a program, okay, so the program will be introduced. Well, the input will be here. The program will depend on this state space, and then the Turing machine will write the output in the tape. So this simple thing can already simulate any other Turing machine, given that we have unlimited time and memory. Okay, so algorithmic inference precisely uses those classes of machines. So even though it's not practical, we cannot make those things in practice. They provide us with intuition and bounds on what can be done with this kind of systems. Okay, so machine learning is essentially concerned with the automatization of inference, and this is precisely what algorithmic inference is about in a more theoretical sense. Okay, so algorithmic information is just an extension of Shannon. It is based not on probability but on Turing machines, and the hypothesis class, well, it is Turing machines. Okay, so an example: if we have a very long set of sequence, it is intuitively clear that we can compress, meaning that we can understand those sequences much easier than this one. Okay, if we wanted to send this one to another person, we would need to essentially send this bit by bit because it looks random. But if we know the underlying program generating this sequence, then it is much easier to send this sequence. It's much easier to compress it. Okay, so this is for instance the binarized version of the digits of pi. So knowing the program of pi allows us to compress this sequence a lot. Okay, so this is precisely the intuition behind the definition of the Kolmogorov complexity, which is defined as the shortest program that can output the object that we are interested in. So this is an uncomputable thing. We cannot in general compute this, but it is nevertheless a useful notion to have. So it is always defined up to a constant. Okay, so Kolmogorov complexity depends on the Turing machine that it is being defined on. Okay, so here we have the simulation constant that is an extra. This constant can be neglected for infinite strings. So this is an important thing. Solomon induction uses all of what I have talked about it now, and it essentially entails finding the best set of theories, programs, hypotheses, however you want to call it, for the given set of evidence. Okay, so this is a very general method. It assigns a measure. Well, it's a semi-measure, meaning that not all those probabilities add up to 1, because some will enter in infinite loops. But well, this is an example. For instance, this would assign a measure 1 to a sequence of head, head, tail, head, head, tail, head, head. Okay. And we can use this thing to build the universal probability, which is a weighted sum of probabilities of the evidence. Okay, and this is an implicit way to say that we are searching over all programs, and we are summing over those that have the most contribution to the overall search. Okay. Okay, so if we assume that there is a true computable process that generates this evidence, then we can actually, well, Solomonov showed that there is a constant bound on the error that we will make after some evidence is given. Okay, as this evidence x tends to infinity, and we keep this a, which is the string that we are trying to predict constant, then this error will be bounded by the complexity of the underlying process generating the data. Okay, so this is essentially it, and it uses the Bayesian method. Ways to make it computable. We can either use we can penalize for the time it takes to run the programs. Okay, so by using the logarithm of the time, we avoid the computation of infinite loops, and this way we can make the search computable. It is okay. This is a way. This is not really feasible because we are searching over all the programs, so it is not feasible. But some approximations are currently being done, and this is the way that machine learning does it. Okay, so in deep learning, what we are interested in is minimizing this code length, minus logarithm of probability as a code length. So we are interested in minimizing the length of the program that we are using and the evidence encoded by this program. Okay, so we are minimizing this thing. So what additional assumptions do we have to do? Okay, notice that this thing is actually the most contributing mode of this sum. Okay, this sum. This is the logarithm. So it is the most relevant mode of the sum. So what additional assumptions do we have to do? Because we have a Kolmogorov of complexity here to make this computable. So the additional assumptions, we can upper bound this Kolmogorov complexity using this minus logarithm of the theta, where theta are now the parameters of a given model, which is computable and finite, and it has nice properties, hopefully. So the minimizing this length is actually equivalent to an upper bound also on the marginal probability of bias. So we are going to minimize this thing in deep learning, and now we are going to also assume additional things to make this tractable. For instance, we can assume that the probability distribution, for instance, is causal. The data, sorry, is causal, meaning that every point of data will depend on the ones before. So we will have an increasing window of dependencies along the way. So this is one assumption. Another assumption is that memory is not infinite, so we need to bound this window using a finite memory. So the likelihood at the end of the map estimation that I showed before ends up being this thing, which can again under another assumption that there is infinite data, which is approximately true. We get to a minimization of an entropy. Okay, and this gets all the way back to, notice that using this minimization of entropy, we're excluding rare events, which is a problem in deep learning. We cannot. Okay, so it is difficult to model rare events. We get to Shannon coding theorem, which is essentially a bound on Shannon entropy of the underlying data generating process that we need to assume in order to talk about entropy. Okay, so the compression scheme doing this minimization on the Shannon bound consists of, we would first have all the data, And in order to compress it, what we would do is first compress the parameters of our model using the probability distribution of the model, and then we would compress the data using the parameters that we have learned during this process, right? And then we would compress this data using this. So it would be a two-part encoding scheme. And this way we would also compress the data. Not as much as we would in an algorithmically uncomputable way, but we do get compression. So regularization is this probability distribution. How we do how do we obtain it? We usually assume that parameters are independent from each other. For instance, they can be the synapses connecting the neural network or and we can assume also that they are Gaussian. So using this assumption, what we are essentially saying is that we want the parameters to be as close to zero as possible. Okay, so when we minimize this, and this will essentially be, we want this to be zero, this will increase the bias and decrease the variance, because it is essentially saying that we want to look in a very constrained narrow region of all the parameter space, right? We want to look in a close to zero, essentially. This is actually providing a lower bound on Kolmogorov complexity, because doing this probability distribution is essentially specifying where the parameters are. So it's easier to compress them, to specify. It is making things simpler, to say it one way. So okay, so in deep learning, what we are doing is minimizing this. Well, it's essentially a Lagrangian. Okay, so we have a cost function, and the constraints that we are specifying are on the parameter space are the well, it's the neural network. So deep learning is essentially a way to assume a particular constraint on the parameter space. This is usually implicit in the cost function, but here it is, and the gradient step just is given by this. In particular, particularly useful in this work are the convolutional neural networks, which introduce a nice spatial invariance, which is useful, for instance, for video prediction, image prediction, and so on. So this is our inductive prior, and also another assumption that we make on the class of functions that are easier for this kind of models to learn. So this is another thing. Okay, so latent variable models. Now, changing a focus to a more practical perspective. What we try to do in variational inference is essentially to compress information in a lossy way. We are trying to learn some latent distribution, a distribution over latent vectors, and we do it encoding first the data and then decoding it back to the data set and looking for an error there. Okay, so if we didn't have this term, this would be just a regular encoder-decoder architecture where we would look for a latent Z and decode it back. If we have this thing, we are actually telling how this thing should be organized. Okay, so we are imposing a structure over the latent space. We are doing this because we don't know how to do this efficiently, because dimension is very high in image space. So we need a way to lower bound this quantity, and this is why we get this elbow lower bound. So this is essentially a way to do coarse graining. Using learning the function essentially to do coarse graining. So we don't even need to worry about the way in which we do it. So in variational autoencoders, those are a particular way to do this kind of variational inference, Bayesian inference. We assume a particular structure in the latent space here, and we impose it to be Gaussian. Okay, so we are saying that we are going to compute the mu and sigma for this for every input that we have here, and then we are going to sample from this distribution using an external noise, okay, given by here, and we will reconstruct, given this latent code, this compressed representation, this coarse graining, the true image back again. So this is a way to do it. In vector quantized autoencoders, it is a very similar notion to do it, but we instead use a convolution neural network for the encoder and the decoder, and it builds us for every spatial location we have a vector. Okay, so for every spatial location we will have a tensor, and this tensor we are interested in. For each codebook for each vector in this codebook, we want to substitute it back in here. Okay, so we are compressing the information in here in the sense that we are using only these codebooks. So once we have done this substitution, we reconstruct back the image. And since this operation is non-differentiable because we are hardly selecting one of the codebooks, we get back the gradient straight through the encoder, and we train the network separately, the encoder and the embedding space. So just to show you a bit the math, what we are doing is taking the argmin between the encoded embeddings and the encoded embeddings and the codebook vectors. So we are taking this argmin, we are substituting back, and then we are passing the gradient straight through. So this is the loss function. This is just a reconstruction, and those are the two terms that make the codebooks closer and to the latent space, the vectors, let's say. So okay, so how can we relate this to the Hopfield networks? Hopfield networks are a way to make a network converge to a pattern. This is essentially the Lyapunov. It is a Lyapunov function. It will always converge to a local minima. So this is the energy of this function. We have an update rule, and this is the energy function. So we can use higher order interactions in this energy function in order to make it converge a lot faster. And doing this, we precisely obtain the transformer, well, the key of transformer architecture, which is the softmax. Okay, so just to put an example, if we have here a phase and we have those would be now the codebooks, what we will do is select the softmax of those phases and obtain well the reconstructed image back. So this is softening the quantization step that we had before, and by doing this, we are introducing this term, which is just the Kullback-Leibler divergence of this prior, which is uniform over all the codebooks. We don't have, and we get this divergence, which notice that it depends now on the beta parameter, which is a temperature. So we have this free parameter, and we also have this regularization parameter here. So this is now the loss function that we get using this. Okay, so how does this new method perform? So this is just here for completeness, but what we are interested in now is looking first at the performance, and second at the perplexity. The perplexity is a way to characterize how many, well, it's an order parameter, how many of the codebooks are being used. If the codebooks being used are more than another, well, the more codebooks are being used, the richer is the latent space, so the better, because it is easier for downstream tasks to generate images or generate more data. Okay, we are increasing the richness if we increase this parameter. So it can be seen, well, varying the temperature of this model, that for higher and lower and very low temperatures, this doesn't work quite well. But here we find the sweet spot by varying the beta parameter in exponents of 2. We find a sweet spot here in the validation test. I think it's clear. It's this kind of curve, and what we will be doing is comparing essentially this model in this range of temperatures to other models that have been proposed. So here is the average codebook usage, and we can see that if there were 32 codebooks, most of them are being used for a quite long range of temperatures. So this is a useful thing to have. Here we see also a phase transition. If we increase the beta parameter during training, here we can see that if we increase the beta during training, the phase transition usually is around beta equals 8, and we can see it for any increase in beta. And what I did also is to keep increasing the beta to 330. And what we see is that there is another phase transition after this point. This means that it's like the beta parameter is making the process act first like something like a gas, then something like a liquid, and then it suddenly crystallizes and it doesn't learn anything. It's very hard to learn anything. So we are operating in this liquid phase, let's say. Okay, so how does it compare to other architectures? Well, first we have here the proposed methods in the paper. So we can see that the errors are essentially the same along any architecture, but in this way, when using the Hopfield network analogy, we get a larger, what we can see here in the training curves, we get a larger codebook usage, right? Which is indeed increasing the richness of this latent space, and it's a good thing. Okay, we can also see this this thing going on in the if we increase this is the number of codebooks and this is the dimension of the codebooks. We can still see this if we increase the dimension. So it's a nice thing. If we moreover project the dimensionality of this latent space that we have learned into a 2D dimensional space while preserving the local topology of this space, this is called UMAP. What we get is that in those other techniques, what happens is that the code books cluster together, and this prevents them from learning much of the parameter space. Instead, here, what happens is that code books tend to occupy more of the parameter space. So, well, this is a thing. Now, in hypernetworks, what changing a bit now the theme, what we are doing is a prediction task. In deep learning, we were training a neural network using a loss function and propagating it back, learning those weights. Okay. In meta learning, in particular in hypernetworks, what we are doing is using a primary network to produce the weights of this architecture, so that this architecture can now do the task and have a loss. Okay, so it's like an extra step, and this extra step makes the model more flexible. Okay, it makes it. We will see now what I mean by flexible. So the task of interest in this work is trying to predict the next frame of this data set. So what we do to predict the next frame is to encode every frame using an autoencoder. This autoencoder is shared for every frame. This is the proposed architecture, and then what we do with the latent vectors over here is we encode them. Well, we compute the phi using this primary network, and these parameters are then used in the hyper network, which uses the last latent representation to provide a rule. This is computing a rule under which this thing evolves, and then it produces this thing, this complete representation, which decodes back into the true frame. So it is essentially a way to, given a set of evidence, we are computing a rule under which this last frame is evolving. Okay, so this is the idea, and this is just the composition of functions all along the way, which finally get subtracted from the true frame, and then we have here for every autoencoder decoder, we are minimizing the loss, the regularization time there. Okay, so this is one. How does the hypernetwork work exactly? Well, there are lots of details, but I'm just going to try to gloss over it a bit. It is important to preserve, essentially, the main point is to preserve locality. So if we have a latent dimension, well, those are the encoded blocks, the encoded tensors, and we have this latent vector here in this spatial dimension. What we are interested in doing is in not losing this locality, because we don't need to know here what happened here to predict the next image over here. It would be a loss of resources. So what we do is preserve locality in those transformations of tensors, and this is the primary network, which essentially extends these tensors in this direction. We get the last representation. We unfold it. Unfold meaning that we just expand in this way. I think it's very intuitive visually. Then we reshape those things so that we can do what's called a spatial-wise CNN. So for every in convolutional neural networks, we would get a filter, the same filter for every spatial location. Here we are computing a filter for every different spatial location. So we are getting the last latent representation this way. Okay, so well, now let's go through the experiments, see how this performs. Again, for completeness, those are the parameters. So the comparison here is done. If we here do not do this, Okay, if we compute the models, if we train this model directly using only this, okay, without using all this primary network thing, we learn directly the parameters, and we get this. Okay, so we can see that by learning a primary network, well, learning the parameters through a primary network, and we are able to reconstruct the digits pretty more accurately than if we only use a usual deep learning technique, let's say, because it is adding some flexibility, as this is the notion of flexibility that I was referring to. So okay, so I think this is very visual. So the conclusions I have finished essentially the deep learning and algorithmic information theory are related essentially through the meaning description length principle, which is taking the highest mode of the universal probability distribution. The assumptions have been made clear, I think, and I think they are somewhat useful for maybe future research. And so there is also a connection between Hopfield networks and Bekovice, and this connection can be used to increase the representation capacity of the latent space. And finally, we have seen that the hypernetworks can be successfully used to predict next frames, so increasing flexibility. This is the bibliography that I have used, and thank you very much for your attention.
So it's time for us to ask some questions. So I would like to start by maybe asking. Okay.